Welcome to today's webinar. The topic for today's webinar is energy storage interconnection, challenges and solutions. We are very excited to have a few guest speakers with us today. This webinar is being presented by the Energy Storage Technology Advancement Partnership, also known as STAP. STAP is a collaboration between the U.S. Department of Energy, Office of Electricity, Sandia National Laboratories, and the Clean Energy States Alliance. Before we get to our guest speakers today, I would like to go over some webinar logistics. If you would like to open and close your control panel, there is an orange arrow that you see circled here. If you would like to submit questions, there is a drop-down menu to the right. Please try to submit your questions during the webinar, as we will save 15 minutes at the end to get to everyone's questions. And finally, this webinar is being recorded. We will email you a webinar recording within 48 hours. This will be posted on CISA's website at cisa.org/webinars. And now I would like to hand it over to our moderator for today, my colleague Todd Olinsky-Paul.
Thanks, Zareen. Welcome to the webinar, everybody. And I do apologize for the delay. We had some technical difficulties, and I appreciate you being patient. I will make this quick so that we can make up a little time. Clean Energy States Alliance is celebrating 20 years of state leadership. We are a nonprofit based in Vermont. We work with state energy agencies across the nation, helping them with their clean energy programs and policy. Next slide, please. We conduct many different types of projects with our state members, and you can see the logos of the members here. Next slide, please. One of the projects that we do conduct is called STAP, the Energy Storage Technology Advancement Partnership. We've been doing this now for over a dozen years, and we have produced many webinars, among other things. Whoops, thank you. In the STAP program, this webinar is actually something of a follow-up, because we did almost exactly 1 year ago, we had an STAP webinar looking at some of the issues with interconnection and energy storage. And I'm happy to say that we are back with a follow-up in which we will hopefully look at some solutions to the problem. In any case, STAP is conducted under a contract with Sandia National Laboratories with funding from US DOE Office of Electricity, and we're fortunate enough to have Dr. Emery Jouk from DOE here today with us. And he'll be doing an introduction in a moment. Next slide, please. So, as I said, Dr. Jouk is here. We're also going to hear from Diane Baldwin from Pacific Northwest National Laboratories, Michael Ropp from Sandia National Laboratories, and Will McNamara, also from Sandia National Laboratories, and Charlie Vartanian from the Institute of Electrical and Electronics Engineers. And I'm Todd Olinsky-Paul with CISA. Next slide, please. Is Dr. Jouk able to make his introductory remarks?
Yeah.
Very good. Okay.
I'm ready.
I'm going to go off screen and you go ahead.
Oops.
Dr. Jouk, you're connected?
Happened. Yeah, something else happened.
All right, we can't hear you, Dr. Jouk, so you can go ahead.
Okay, how about now?
Yes, we can hear you.
Okay, well, interconnection. It's one of the more important issues facing energy storage, as well as all new generation. The backlog of new power generation and energy storage projects seeking transmission grid interconnection in the US grew by 30% in 2023 to nearly 2,600 gigawatts. This is more than twice the total installed US power plant capacity. Solar battery storage. Something else is coming in.
We can hear you, Dr. Juk.
Okay. Solar, battery storage, and wind accounted for over 95% of this interconnection queue backlog. However, this growing backlog has become a bottleneck, with lengthy study processes and most requests ultimately being canceled or withdrawn. The Federal Energy Regulatory Commission adopted major interconnection reforms in 2023 to address this, but their impact is yet to be seen. Some of these reforms include cluster studies. Instead of evaluating projects individually, multiple projects are grouped together for analysis, reducing study times and costs. Readiness requirements. Stricter readiness requirements, such as higher application fees or site control requirements, are being implemented to discourage speculative projects and ensure that only serious projects enter the queue. Queue transparency. Improved transparency measures, such as publicly available queue data and regular status updates, are being adopted to provide stakeholders with better visibility into the interconnection process. And finally, cost allocation reforms. Revisions to cost allocation methodologies are being explored to ensure fair and equitable distribution of upgrade costs among project developers and other stakeholders. Against this background, energy storage pricing fell significantly in 2023, with lithium-ion battery system costs dropping from 270 per kilowatt hour in mid-2022 to 180 per kilowatt hour by year end due to falling lithium prices. This pricing decline is expected to further propel energy storage deployment and therefore make the queue longer. The US West region outside California had the largest interconnection queue at 706 gigawatt, followed by the California ISO at 523 gigawatts as of the end of 2023. Over 1.2 terawatt of would-be projects joined interconnection queues after the Inflation Reduction Act passed in 2022, including 540 gigawatts of storage. If you look at interconnections over the last 30 years, you see much activity on the Pacific coast, in the mountain states, in Texas and Florida, in Chicagoland, and in New England down to, say, Pennsylvania. The rest of the states are apparently content with legacy fossil fuel systems. And that's all I will tell you, and we have many interesting talks following this. Thank you.
Thank you, Dr. Juk. And again, I apologize that we did not have Dr. Juk's slides visible. Do we have the next deck? Can we get that on screen? Okay, thank you. So I'm just going to expand just a little bit on what Dr. Juk just presented with hopefully some visuals to help you see what we're talking about. And then we will go on to the following speakers. So this was just meant to be an introduction to the problem. And this is, I'm doing this so that everyone else, the other speakers here, can really focus more on details and solutions. And this is sort of a laying the groundwork. And I want to just mention that there are a couple of publications, if you're interested in this topic, Last year, Clean Energy Group published the Interconnection Bottleneck Report at the top, and then also IREC published a very good report, Thinking Outside the Lines, which you see at the bottom there on the right side of the screen. Oddly, they're almost the same color, but totally different reports, which, interestingly enough, come to many of the same conclusions. So they're both available for download, and I recommend them. Next slide, please. So let's start with national interconnection queues, and then we'll try to zero in a bit on the state and regional queues. As Imre stated, capacity in the queues has quadrupled in 12 years. And of that capacity, the most dramatic observation here is that solar and energy storage capacity in these queues has grown dramatically. When we say queues, what we're talking about is the waiting list of proposed projects that are in a line waiting to be studied in order to gain interconnection onto the grid. So before they interconnect, they have to generally undergo a study, either done by the regional transmission authority operator or the local utility, depending on whether it's a transmission or a distribution connected project. And so those studies are typically done one at a time, unless there are cluster studies, which are being tried in a few places. Even so, these queues can be a year or 2 years long. And so it can take that long just for the study to commence. So when we talk about queues, this is what we're talking about. You can see compared to the 2 years shown here between 2010 and 2022, the solar in the queue in 2010 was tiny, and there was no storage to speak of in the queue at that point. By 2022, you can see there's quite a bit of solar and quite a bit of storage. It's grown dramatically. Unfortunately, just 14% of queue capacity reached commercial operation in the years of between 2000 and 2017. Next slide, please. Looking a little bit more closely, we can look at PJM, which is the nation's largest regional transmission organization. It's mid-Atlantic and part of the Midwest area. The PJM interconnection queue doubled in capacity since 2019. Costs of interconnection have increased dramatically from the period 2000 to 2009, when median costs of interconnection were between $18 to $30 per kilowatt. And from 2010 to 2019, they're up to $8 to $85 per kilowatt. And these cost increases are driven by network upgrade costs. In other words, the cost of upgrading the grid to accept the newly interconnected technology. And interestingly, the interconnection costs aren't the same for different technologies. So the cost of interconnecting storage, solar, and wind far exceed the cost of interconnecting natural gas. So you could see that in the bar chart here, where the interconnection cost of natural gas is $24 per kilowatt. The interconnection cost of energy storage is $335 per kilowatt. Again, this is in PJM during a specific period of time. Next slide, please. This is just another way to look at it. And what this, I think, is showing is that there's a correlation between cost and project completion. So complete projects on the left tended to have a much lower cost for interconnection than withdrawn projects on the right. And that's because if your economics for your project are or good but not phenomenal, and it turns out that you're going to have to pay a lot of money to get interconnected because you're paying for a grid upgrade of maybe $1 million, something of that sort, it may completely kill the economics of the project, or you may simply lose financing because you're waiting so long in the interconnection queue. Next slide, please. So down to the state level. And this, we're looking at Massachusetts because we happen to have information from another report that we did on Massachusetts. And as you can see, again, the vast majority of the queue is solar, storage, and hybrid, which is a combination of solar and storage. And these projects make up 93% of the interconnection queue. There's virtually nothing else in the queue. So these queue delays and interconnection costs really affect the ability of states to meet their decarbonization goals and their renewable and energy storage targets. If you can have the best programs and policies in the world, but if projects can't get interconnected onto the grid, then they're not going to be built. Next slide, please. So this is kind of interesting, and it just shows you how dramatically this affects the ability of projects to actually be built. The top chart on the right is showing proposed projects and authorized projects. So, for example, if you look at 2022 on the right side of that chart, proposed hybrid and storage projects, that's energy storage and hybrid solar and storage projects, were at about 400 megawatts of capacity that year in the queue. And authorized projects were close to zero, in fact, have been close to zero pretty consistently. Now, they're not at zero. This scale is a little bit coarse and it's hard to see fine gradients here, but you know, they're in the single or low double digits in terms of megawatts. And that's been pretty consistent. On the bottom chart on the right, you can see that the number of incomplete and withdrawn applications is rising and the number of complete applications is falling. And that represents a huge loss of investment. In fact, the proposed capacity waiting in the Massachusetts interconnection queue when we did this study represented approximately $8 billion in planned investments. That was in 2022. So for that many of those projects to be withdrawn represents a huge loss of economic activity. Next slide, please. So a few takeaways, and then I'm going to let others who are better informed about possible solutions get into the act and make their presentations. One problem is who pays? In other words, if you are proposing an energy storage project and it's going to require an upgrade to the local grid, and that's going to cost $1 million or $2 million, who should pay for that upgrade? Traditionally, the model for this is something called cost causation, meaning that if you cause the required upgrade, then you pay for the required upgrade. And that means that the whoever's developing that project has to bear that cost. There are other ways to pay for grid upgrades. For example, the people benefiting from it could pay for it or could share the cost. Ratepayers could share the costs. In cluster study situations, numbers of projects in the same geographical area could share the costs. So there are different approaches being tried, but that is a big issue. The way that grid upgrades are planned is another big issue. Typically, the grid upgrade is done in reaction to a proposed project and not in a more holistic way, especially this is true for distribution grids. There's not a whole lot of holistic distribution grid planning where you look at where we think there will be a need for example, solar and storage and wind, and then we plan for that. So the grid upgrades tend to be reactive rather than proactive and local rather than systemic. Finally, there are problems with the way that energy storage is incorporated into interconnection protocols, and that's because most of the protocols were developed prior to storage being something that utilities really thought about or needed to think about. And so the operating characteristics of energy storage are really not accounted for in a lot of these legacy interconnection rules. And so worst case scenarios are often assumed. And that often results in higher costs. Next slide, please. Okay, well, that's it for my introduction. I hope it's been helpful. I will pass this over to the next speaker, And I want to remind everyone to please type your questions in as you think of them. We'll get to as many as we can at the end of the presentations. Thank you.
So I guess that's me. I am the next speaker. Hello, everybody. This is Will McNamara with Sandia National Labs. It's a pleasure to be with you here today. I'm going to try to pull up my screen. Let me see here. Can you send that cue again to me, Samantha, to show my screen? Or are you seeing my screen?
We're seeing your screen if you put it right in slideshow mode. Yep, perfect.
Excellent. Okay. Well, I am a grid energy storage policy analyst at Sandia, and so I approach this topic from the policy perspective. That's going to lead us into a discussion around some of the solutions that are at play, and raising this question of whether or not policy can address the types of challenges that we've been talking about. My entry point into this conversation is decarbonization. I'm certain that most of you are familiar with the term, but for those who may not be, decarbonization is essentially the move away from what has been a historic reliance on fossil fuels to an ever greater reliance on renewable energy and clean power. Now, you'll see that 19 states have adopted very aggressive decarbonization goals with very aggressive timetables. How are they going to get there? They're going to get there through renewable energy projects that have to go through interconnection queues, and hence the types of challenges that we're talking about. Decarbonization as a concept and for our country is going to require unprecedented amounts of new renewable projects. As Dr. Zhuk had indicated, we're seeing a significant amount of new clean energy and renewable energy entering the queue, representing just record-setting levels of projects that are needed if we're going to achieve our decarbonization goals. The 2 terawatts that were calculated in 2023 represents a 3 times greater level than what was seen in 2022, in just a year prior. And of course, we are talking about storage, solar, and wind projects. Now, on average, the time in the queue is around 5 years, and that is a trend that we see across the country. So regardless of region, there's an average of sitting in a queue for 5 years, if you can imagine how frustrating that might be for project developers. You can see where the concentration is taking place on this map, thanks to Lawrence Berkeley Labs. I want to be clear that interconnection is an issue at both the state and the federal level. So when we talk about the state level, we're primarily talking about interconnection at the distribution grid. And when we're talking about federal policy, we're looking mostly at interconnection at the transmission level. So we have regulatory oversight coming from the state public utility commissions at the state level, and primarily FERC at the federal level. Very interesting report that I found. I've given you the link here. This is fascinating information that unfortunately I don't have time to delve into, but if you take advantage of this resource, this is data that's been compiled by the DOE, and it shows you the projects, the numbers of projects that are in each state's queue. And so this is a national problem. You can see that the queue backlog is really occurring in every state, some more significantly than others. There are over 1,200 projects in the queue in Texas and 947 projects in the queue in California. Those certainly represent the extremes. So I want to talk a little bit more about what are the issues that we are facing that both create the policy landscape and what are some operational issues that are impacting this, this situation. So from a policy perspective, at the highest level, what we're looking at are either non-existent, ineffective, or outdated policies. And that is preventing distributed energy resources, including energy storage systems, from getting connected to the grid, and therefore maintaining reliability and resilience and helping us reach our decarbonization goals. In many jurisdictions, energy storage is not even explicitly included in definitions of generating facilities or the entities that would be eligible for getting connected to the queue. Examples of this would be Florida, New Hampshire, Ohio, and Washington State. In addition, interconnection rules don't always adequately reflect the capabilities of energy storage, and that has an unfortunate result of limiting the opportunities for applications and benefits that storage can provide to the grid. Now, due to these inefficiencies and complexities in the process, on average, 70% of projects may end up getting withdrawn from the queue. And as Todd said, that has tremendous economic ramifications. It erodes our pathway to decarbonization. And it's so inefficient, to say the least. And it is a condition that has to be addressed. Now, as I mentioned, we're talking about both distribution interconnection and transmission interconnection, and they are interrelated because as a project gets interconnected to the distribution grid, it very well may have reliance on power sources coming from another area, and therefore it is also impacted by transmission capacity or the lack thereof. So it is a condition that really permeates regulatory jurisdictions as well. Now, when we look at the last year, 2023, this map shows you that state activity to update interconnection rules remains very limited. This map is mostly gray, and that indicates that most states have not taken the steps to update their interconnection rules to specifically address energy storage. Now, there are policy issues and there are operational issues, and they also go hand in hand. From an operational perspective, when we talk about energy storage systems, there are variations in export levels. We have some systems that don't send any electricity back to the grid. We call those non-export systems. Others may be designated so that there are limits on the export levels at certain times or certain limits, and we call those limited export systems. And then we have situations where there are inadvertent exports, power that's unintentionally exported from a distributed energy resource when load drops off suddenly, and or the export control system responds to a signal, and that can wreak havoc on the electric grid as well and have very significant ramifications for frequency regulation and other factors. This is a huge operational issue for utilities because they are in charge of maintaining the safety and reliability on the grid at all times. There's also a concept that we refer to as hosting capacity. At any given time, the electric grid can only accept a finite amount of power coming from exports from connected systems. And the utility has to have a direct line of sight into the available capacity on their networks. This is known as hosting capacity, and it relates to hosting capacity analysis. It's a very sophisticated undertaking, and I think it's fair to say that the majority of utilities are still lacking the tools that are required to have that very granular level of insight into their hosting capacities. Furthermore, there's a lack of agreement around what are the acceptable methods for controlling exports back to the grid. We don't have a uniform approach across the country. This is another map that shows you a lot of white space, and it's meant to indicate that these states that are in white do not have robust or sophisticated hosting capacity and analysis in place. So it's still very much the exception rather than the rule. Back to the policies at hand that are my key focus area, we have this lack of inclusion of storage in interconnection rules. Many states still do not mention energy storage at all in their interconnection rules. We have inconsistent standards regarding those acceptable methods that can be used for controlling exports. There's a lack of defined rules and processes for evaluating operating schedules, the schedules in which an energy storage system can operate on a predetermined schedule. There is a lack of differentiation between standalone energy storage projects and those projects that are conjoined with solar projects. There's a very solid argument that can be made that they should be treated differently and perhaps expedited with some projects over others. And furthermore, there's a real need to continually incorporate what are the interconnection standards that are being developed by the industry, the IEEE 1547 standards. There are many states that have still not taken that step, and that is a gap that needs to be addressed. Now, the Interstate Renewable Energy Council had a very interesting study in the last year, and they looked at all of the states and their interconnection standards and gave them all a grade. Of the 39 states that have statewide interconnection procedures, not necessarily specific to energy storage, but just have an interconnection policy in place, only one state, New Mexico, received an A for its interconnection rules. And the reason for that is that New Mexico was the first state in the country to adopt a screen to evaluate the impacts of that inadvertent export that I was talking about. 6 states received a B. The remaining 32 states received a grade of C or lower, and 13 states have not adopted any statewide interconnection rules and therefore automatically received an F grade. So you can see there's a lot of work to be done, and that is due to analysis conducted by this independent agency. So the overall result that you're going to hear time and time again today is that the appetite for storage is much greater than the ability to build it, and the ability to build it is greatly compromised by these interconnection issues that we're talking about. On the positive side, there are remedies in place, and so I'll go through these quickly. The best practices at the state level really do involve the updated standards and export provisions and streamlined review processes. California stands out. They've done a lot of new work in this area. I think I just lost my screen. Can you still see my screen, Sam?
We can still see it. It's
Okay.
not in presenter mode anymore, but we can see your title
All right,
slide.
let me get back to that. Sorry for the delay here. Okay. Sorry for that mishap. California stands out as a leader. The CPUC in California in March of this year established new regulations around what we're calling limited generation profiles. These are putting limits on the amount of energy that distributed energy resources can send back to the grid at different times. They are the first state that I'm aware of that is taking that step from a policy perspective. And this is really important because it's designed to minimize the impact that a renewable energies project impacts the grid, and therefore prevents or defers what would otherwise be very costly infrastructure upgrades. Now, California's policy on this point is really contingent on the fact that the utilities in the state had already been required to develop very sophisticated distribution system analysis with the type of hosting capacity analysis that I referred to. That was needed in order to have that level of control over the devices that the CPUC has now put into place. This measure that's just come out from the CPUC adds upon what had previously occurred coming out of the California ISO. And they had established giving cluster approvals and giving expedited approvals to project for priority projects. So California really does stand out in that regard. Other call outs that I'd like to mention from the state level is Oregon. Instead of basing their interconnection analysis on the aggregate nameplate capacity of a system, they are now looking at the export capacity and presumably will be defining additional interconnection policies on that basis. New Jersey is looking at capacity-based fees that are related to the interconnection queue. I think within the concept of, again, giving priority to certain circuits, certain distribution lines that are more critical, and charging accordingly to access those areas. Now, other utilities in other states, Duke Energy and Xcel, are also adopting this kind of cluster approval approach instead of looking at projects on a case-by-case and first come, first served basis. This is very consistent with what we now see happening at the federal level. FERC just 2 weeks ago released its Order 2023. This is the first major change to transmission interconnection requirements in the last 2 decades. The FERC order requires transmission providers to adopt a first ready, first served cluster study approach when examining what grid upgrades may be needed to therefore drive the projects coming in for approval. This is a very significant change. It's replacing what had been the legacy approach of studying individual proposals on a first come, first served basis. FERC is also increasing the financial commitments for interconnection projects so that they have more stake in the game. Hopefully that will lead to less projects being withdrawn. But with that financial commitment, the projects are demonstrating that they are truly committed to getting this project completed. Also significant in the FERC order is that it's allowing projects to co-locate on a shared site behind a single point of interconnection and share a single interconnection request. This is pretty significant because it's removing what had been barriers for these co-located resources, and it's creating a more efficient, standardized approach to get these projects approved. So that is a quick overview for you of what's happening from a policy perspective. I, of course, want to thank Dr. Zook. He supports all of the work that I'm doing and is the sponsor with his funding through the Department of Energy Office of Electricity. With that, I will turn it back to Todd.
Well, thank you, Will. I will just simply invite the next speaker to go ahead and start their presentation.
Good afternoon, everyone. My name is Diane Baldwin. I am a project manager with Pacific Northwest National Lab. For the last 18 months or so, I've been involved in a project funded through the Solar Energy Technology Office and Wind Energy Technology Office called the Interconnection Innovation Exchange, I2X. And I'm excited to share with you some of what we've been doing in I2X, which includes creating roadmaps with a lot of solutions and identifying paths forward for all the different stakeholders who want to effect interconnection reform and want to get a more robust, streamlined, efficient process that results in more projects getting onto the queue and overall cost efficiencies. So we'll jump in here. I'm going to, you can go ahead and advance the slide. I'm going to go pretty quickly through this, given that we were, a little bit slower to start at the beginning. So I may not spend 5 minutes on the overview, but I do want to give you just a little orientation to what's going on in the I2X program, because there's a lot of opportunity for you to engage with us. And I'll get into specifics of the roadmaps that we've been developing. And then I think we're going to hold all the questions until the end. So go ahead, next slide. So the I2X program overview, next slide, please. I think we're going to skip this one. Basically, you know, same sort of thing that you've been hearing from other presenters. We need to accelerate getting projects on the queue and getting them out of the queue and onto the system. And interconnection is identified as a pretty significant bottleneck at all levels. One of our key outcomes from the I2X effort is a 5-year strategic roadmap. This is a really complex space. There are a lot of challenges. They have multi-dimensions. We can imagine solutions that cannot be implemented by just one group of stakeholders. We all have to work together on this. And so developing this 5-year strategic roadmap has been a pretty comprehensive effort that started with a lot of stakeholder engagement. Next slide, please. So we identified these target groups of stakeholders and reached out and engaged people to participate with us. You can sign up. You can go to energy.gov/I2X and you can become a member of I2X. You can identify yourself as belonging to one of these stakeholder groups, or you can just join as a generally interested party. We have had a number of online collaborative working sessions that we called solution exchanges on a variety of topics, always looking to highlight the perspectives, the particular needs and challenge points of each of the different stakeholders, and looking again as we develop the roadmap to really bring the voices of the stakeholders into this roadmap content and make it very actionable across all the range of interested stakeholders. Next slide, please. So one of the key aspects that we have engaged in the I2X program in terms of trying to break this extremely complex space down and make it a little more digestible is to acknowledge that, you know, interconnection isn't just one thing. You know, it's not just filling out the application. It's not just getting a study. It's not just signing your interconnection agreement. Interconnection is something that is a process that needs to be top of mind and can be a significant hurdle to overcome related to all these different steps of project development. So in addition to needing to think about interconnection and how it's a factor all the way from site selection to commissioning your project, there are also different sort of qualities of the interconnection challenge that are distinct from each other. Some of the challenges that we identify are particularly about the technologies and the engineering, some of the things that Will just touched on, you know, these ideas of export limits and how to avoid inadvertent export, how to apply the correct standards and encourage standards adoption. Some of the challenges with interconnection are administrative. You know, how are the queues themselves administered? Is there any automation? Are things like interconnection applications, are they entered by hand? Are they still, you know, forms that you fill out and send in the mail? Believe it or not, that is still the case in some parts of the country. And then, of course, the market and the regulatory aspect. We can't move ahead with some of the reforms that we would like if we don't have the underlying supportive regulations. Now, the flip side of that is progressive regulators like state PUCs that want to move ahead with innovative reforms can sometimes be a bit stymied by some of the technical and engineering concerns that are brought up by the operating utilities. So that's a good example where we have to work together across this space and be mindful that the solutions that we're talking about have all of these different dimensions to them. Next slide, please. So as I mentioned, I2X has had a really significant stakeholder engagement. We had a whole season of these online interactive collaborative groups. We called them solution exchanges. We wrapped those up in last summer of 2023. Right now, we've really been focused on the strategic roadmaps. The first one, Volume 1, which applies to transmission level interconnection, was published and final in April. So again, if you go to energy.gov/I2X, you don't have to sign up to be a member if you don't want to, but you can navigate there to the Volume 1 a roadmap, which again is highlighting solutions really aimed at all the different stakeholders addressing these three different elements as I highlighted, you know, technical and engineering challenges, market and regulatory challenges, administrative challenges, and how we can work together across all the stakeholder groups to make progress. We are currently, PNNL is the lead lab, currently developing a DER interconnection roadmap, and we're developing distinct solutions in some cases from those solutions that are workable at the transmission level, developing that draft content now. It will be published through a request for information process. So we really are looking for robust stakeholder feedback. If you've been part of I2X up until now, put a little tag in your calendar. In July, we want to hear your feedback. If you're hearing about I2X right now for the first time, still put a tag in your calendar. In July, we would love to hear your feedback. So very specific solutions that we'll be highlighting with specific actions on the parts of regulators, utilities, vendor community, research community, NGOs, energy and equity justice advocates. We want to have all of your voices heard as we'll then push to finalize this DER interconnection roadmap by September. Just a quick shout out to all of our lab staff. We've got collaborations with Sandia National Lab folks, NREL, Lawrence Berkeley Labs, and PNNL staff who are all working doing targeted technical assistance. And this is like a chance for us to kind of test drive some of what we have as solutions in the roadmap and working with actual stakeholders, PUCs, utilities, vendors, and really helping them to see what are the challenges of implementing some of these innovations. So the learnings from those are incorporated into the roadmap. Next slide, please. Snapshot, I won't spend any time on this other than to say a lot of engagement. Over 2,000 attendees grouped together over our first season of solution exchanges. We do plan a second season of solution exchanges after the roadmap's complete. Next slide. So as I mentioned, we've got the distinction between the transmission-focused roadmap and the distribution-focused roadmap. We highlight solutions that address queue management, cost allocation challenges, grid engineering, data transparency. Woven through the roadmap are, in addition to focusing on those challenges that are in the red in this graphic, also what do we need to do in terms of the workforce and training to accommodate this, you know, sea change in terms of, you know, the number of applications to apply to get interconnected both at the transmission and the distribution level. And then how do we make sure that equity and energy justice are achieved through these pretty significant interconnection reforms that we're all undertaking. Next slide, please. So let's just jump into this roadmap overview. Next slide. So I've got 4 top-line goals that are present in this roadmap. You'll also see these in the transmission volume, which, as I mentioned, is final and available for download, energy.gov/I2X. Increase data access and transparency. If we can make data about what the grid conditions are presently, who else is in the queue, what kind of costs those interconnection studies for current and prior queue applicants, what kind of studies were identified in their interconnection queue, interconnection study processes, we can really inform developers a lot better about where to put in an application. So we heard that we see the number of completed applications going down and the number of incomplete and withdrawn applications going up. That means overall the process isn't really working. And what we've heard from developers is that because they don't have this increased data access and transparency, sometimes they'll submit quite a number of applications. They're really seeking information by submitting the interconnection application. They intend to develop one project, but they're putting in 5 or 8 applications because it's the only way to really get information about the cost of the interconnection and the capability of the grid at any particular point. Next slide, please. So under that first goal area, increasing data access and transparency, we have some really detailed content about establishing and maintaining these capacity analysis tools. Will touched on this already. Overall, we need to increase the amount of data, the scope of it, the quality, the standardization of data that's collected at the state level. Most of what we were seeing in Todd's slides and also from Will comes from the work at Lawrence Berkeley Labs looking at the Q data at the transmission level. Why is that? Because we have guidance for those transmission operators and transmission owning utilities. What kind of data do they need to provide? So we also provide a solution that builds on work at NARUC, National Association of Regulatory Utility Commissioners, to give everyone guidance. What kind of data should you be collecting if you're not even collecting any right now? How do you address concerns about confidential information, critical energy infrastructure information, and then really how to strike that balance between you want to create value for all the stakeholders, but it does place a burden on the distribution utilities, and it does introduce some risks with that confidential information. So there's several solutions in this part of the roadmap that help to address that tension. Next slide, please. We have a whole section of the roadmap that's about improving the process and the timing. Will mentioned the trend toward group studies, some specific content around that, best practices for implementing that, and specifically for energy storage, how to make sure that the particular study assumptions and parameters that are incorporated into the assumptions about how the unit will operate are adequately and adequately addressed and at the right level of granularity when you're doing a group study where some projects have energy storage and some projects do not. Flexible interconnection is one of the biggest innovations that we see going, really high interest among utilities and developers to understand this. It has some similar elements to the limited generation profiles that Will mentioned. The idea is that you are acknowledging that you can allow a lot more nameplate kilowatts or megawatts of projects to get on the system if they will agree to curtail for a limited number of hours per year. So how do you do those studies up front, come up with reliable estimates of how much energy that developer will have to, go unpaid because they're not permitted to export power during times that they otherwise would have, but how much additional kilowatts or megawatts will you be allowed to put on that circuit? And then as more projects come on, how do you manage the curtailment signals and validate that the projects are curtailing when they need to be to adhere to those flexible interconnection arrangements? Really powerful concepts there. Again, we have technical assistance that's really helping our team to get lessons learned and incorporating those into the roadmap. Generally speaking, we have this tension in this area of the roadmap between making the processes more complex versus really aiming at speeding everything up while still maintaining that accuracy of the screens and the studies. Next slide, please. Cost allocation strategies. Everyone wants to talk about how can we allocate the cost differently. So we give some examples. We support that with examples around the country where these cost allocation alternatives are being explored. Always again with that tension. So the interconnection customer, as Todd said, has historically been the one who has to write the check. If we're exploring other options, preemptive upgrades, making segments of the system where you anticipate that DERs are going to expand significantly, making them DER ready, that does place that cost now primarily on the shoulders of the ratepayers. How do we ensure, a balanced, overall allocation of those costs? And there are some really innovative solutions out there, upgrade funds that are just assessing a flat interconnection cost to every project based on per kilowatt or megawatt. And these are just really getting going. We're taking baby steps. So the roadmap helps to identify what's out there, how all the different stakeholders have collaborated to understand the structure and the risks, and then how those will be monitored for their success moving forward. And an important part here, picking up again on something that Will mentioned, is really clarifying for energy storage that nameplate versus export capacity. We've seen again and again that can really tip the scales in terms of cost allocation in a way that's burdensome on energy storage projects. So the last part of the roadmap, next slide please, that I want to just snapshot real quickly is maintaining a reliable, resilient, and secure grid. We put a tremendous amount of trust in our utilities, that the lights will turn on when we flip the switch, that when there is a grid disturbance, that they'll get us back up and online as quickly as possible, and that their staff who come out and address problems on the grid are going to be safe in their everyday jobs, as well as during times where there are grid disturbances. So this is a real responsibility at the utility level. We want to do things like speed up this process and find better cost allocation strategies and make everything more transparent, but we can't do that if we're sacrificing reliability and resilience and security on the grid. So we have specific content that addresses cybersecurity requirements and recommendations to start incorporating cybersecurity analyses and requirements into agreements. Generally speaking, more coordination between what historically has been happening in the interconnection process and what could be happening more in grid planning processes. And I think this is a perfect segue to hand off to Mike and Charlie, because I know both of them are going to talk more about adopting standards. So I'll just wrap it up there. Thank you.
Excellent. And I believe I am the next speaker up. This is Michael Ropp from Sandia National Laboratories. Were you guys? Yeah, there we go. Perfect. So my topic today is I'm going to talk to you about the 1547 standards, the interconnection standards that Diane just mentioned. Talk a little bit about what they are and what they do for us, and a little bit of what is in them. So this is a little different than what we were just discussing. We're not really directly looking at queue structures and who's going to pay for things and stuff like that. It's almost entirely about setting a minimum set of agreed upon technical performance requirements so that we know if you meet these, the issues of reliability and resilience and all the things that Diane mentioned are actually going to be met. We're going to be able to take care of all of that. So go ahead and move to the next slide, and I'll show you where the different families of standards apply. Oh, I guess first what we'll do is we'll just talk a little bit about what these are for, what good they do for us. One of the main things about interconnection standards is that they provide uniformity of requirements between different jurisdictions. It used to be the case. We have some 3,000 utilities in the United States, and every one of them was setting their own interconnection requirements. We started work on 1547 in the late 1990s, and the first version of it then was published in 2003. And that was one of the main reasons that came into existence at all, was to try to say, okay, look, there is a certain minimum set of requirements that we can all agree to. Some utilities do add to those requirements, but at least then manufacturers, developers, the folks who are trying to come up with this stuff have a target to shoot for. I mentioned before that there's a consensus process. The joke that we tell ourselves is consensus is the state we reach when everybody says, I don't like it, but I can live with it. But the bottom line is we have a whole bunch of stakeholders with different perspectives, all feeding into this and saying, well, this is what we need, this is where we think it needs to go. And there are two interfaces between these resources and the rest of the power system. There's a power interface where we're shipping the actual power back and forth, but there's also an information interface. And when we talk about interoperability between the different resources and between the resources and the power system, we are talking about interoperability for both of these interfaces. So who uses them? They are essential for developers, for equipment manufacturers. Power system operators use them to set policy. The various authorities having jurisdiction, these are the people who make the policy decisions, your state regulatory commissions, and so on and so forth. They often will refer to 1547 or to one of these standards as their reference for where those technical requirements came from. Yeah, I suppose that's about all we need to say about that. Let's go ahead and move on to the next slide, which is the one that I had mentioned before. I want to show you where these different families of standards apply. There are two main families of standards that govern these interconnections. The one that we're going to focus on today is the one that's over on your right in green. That's the 1547 family, and it applies at distribution, so in the lower voltage levels of the system. And it also applies to all sources of active power that are connected to distribution, not just inverter-based ones, But synchronous generators also, if they're connected to distribution and exporting to the system, they are also DERs and they are also subject to 1547. When we get to the higher voltage levels in the system, there's another family of standards, the IEEE 2800 family, which you see in red, kind of the center left here. 2800 applies at transmission and sub-transmission. And it also, you notice it says IBR. 2800 only applies to inverter-based resources, not to rotating machines. So the first 2800 standard was published in 2022 on Earth Day, interestingly. We are right now working on a 2800.2, which we're hoping to publish next year. 2800.2 will establish the tests that one will want to run to ensure conformance with the 2800 standard. You notice the teeter-totter that's down at the bottom of the slide here. There's always a little bit of a balance that has to be struck. When we write these standards, we're trying to streamline the process as much as possible. But in the process of streamlining, we also exclude certain options that could become a barrier to innovation. So we're always trying to strike that balance. We want maximum streamlining, but we want to make sure that we're allowing the market and industry to do what it does best. So that balance is always front of mind for us when we are writing these IEEE standards. So let's go ahead and go to the next slide, and I will show you the 1547 family of standards. And this is a little bit of an eye chart. We're not going to go through this in detail. There are two of these that I want to focus on today because they are directly relevant to energy storage. The first one I want to focus on is that one that's shown in red down at the bottom. So the base standard, the standard that sets those basic minimum technical requirements that we talked about, that's 1547-2018. That's the top row in this table. Then everything else, we call that the base standard for the 1547 family. Everything else then refers back to 1547-2018 in some way. So 1547.9, the one shown in red, is specifically on the application of that 1547 base standard to energy storage that we are connecting to the distribution system. I was one of the two co-chairs of the working group that wrote 1547.9. Let's go ahead and go on to the next slide. So we can talk a little bit about what is in here. And this is, a lot of technical stuff that anybody who's interested in more detail on any of this, do not hesitate to contact me. My email address will be on the last slide here. If you need more details, happy to talk to you about it. But so what 1547.9 is all about then is figuring out how do we apply that base standard specifically to energy storage. So a lot of it is there's just some more terminology that we needed to get straight. The base standard refers to an operational state of charge, but it didn't define it. And any of you who have worked with energy storage will be well aware of the fact that there are many different ways to talk about state of charge. So we talked about that. We talked about the operational capacity. There are some black start aspects. I should call it really cold load pickup. Black start is the term that tends to be thrown around, but you can have an intentionally islanded system that is being energized by energy storage. And if you have excess capacity, we may want to assist in black starting some of the loads around this island. So we talk about that a little bit in 1547.9. It says here, clarifying volt-var support modes. What happened there was in the base standard, it was always the intention that energy storage would be included, but there were a few things that when they were written, they were still a little bit solar centric, pretty much. And this was one of them that when we talked about the reactive power support modes, they only existed, they were only defined for positive output power. In other words, for energy storage, a discharge mode. There was no definition of the volt-var support modes for the charging mode. So we took that on in 1547.9. And then some of the rest of these things are, pretty typical things that would go with energy storage, like for the fast frequency response. It's difficult to really work with fast frequency response when the energy storage is in distribution, because the distribution system just frankly is not designed to support that. So it limits how much active power we can get out of that part of the system and how quickly we can do it. So 1547.9 gives some guidance on how all of that works. I also wanted to just very briefly point out the very last bullet there, V2G, vehicle to grid. That is becoming a fairly hot topic in the standards community. Part of the reason why V2G is an issue is that for certain V2G configurations, in 1547, we have commissioning tests. So when you build a distributed energy resource, or DER, somebody from the utility will come out and go through a checklist and make sure that everything's up and running, and away we go. Obviously, if I have a V2G capable charging system from manufacturer ABC, and I pull up with a vehicle from any manufacturer XYZ, I could be changing that system all the time. I can't have somebody come out and commission it every time. So there needs to be an automatic, some kind of handshaking method that handles that commissioning part of it automatically. Did I just say automatically twice? I just won the award for redundancy award again. But that's what the V2G piece is about. And there's a lot of that going on in the 1547 world. On to the next slide. I wanted to, just to clarify scope a little bit. A lot of people ask, so like if I have a photovoltaic system and energy storage co-located with it, this PV plus storage system, if I control the energy storage, charging and discharging such that none of the PV power goes out onto the grid, then technically that could be considered what Will was referring to before as a non-exporting system. It can still have inadvertent export, as Will pointed out correctly before. But there were a lot of questions about, well, does that actually fall into the scope of 1547 then? If I have a system like this that is controlled not to export power, does it still have to meet 1547? And of course, the utilities on our working group were saying, well, yeah, absolutely, yes. That's a huge loophole if we suddenly said, nope, you're exempt from all of this stuff. So there was an attempt in 1547.9 to get a little bit better handle on what we mean by capable of exporting active power. It feels weird that you would have to define that phrase, but that's really what it boils down to. So you can see the definition is in red here on the screen. But something like an uninterruptible power supply, that's the UPS down at the bottom, that one does not serve load in parallel with the distribution system, with the area EPS, is what we call distribution. So that's out of scope, but the PV plus energy storage does, so that's in scope. V2G does, so that's in scope. This V1G, which is unidirectional electric vehicle charging, it can be modulated to provide system services, but the power flow is always from the grid to the vehicle. That's out of scope because it does not provide active power. Okay, now on to the next slide. Sorry, I keep jumping one slide ahead of myself. So I wanted to very briefly mention to this group another standard that is relevant to energy storage that is being revised right now. We actually are having working group meetings on this standard this week. I had the first half of it this morning and the second half of it will be tomorrow morning. That's this IEEE 1547.4. This is the part of the 1547 family that deals with intentionally islanded systems, what some people would refer to as microgrids. But it's a chunk of the system that if for reliability reasons or for any other reason, we decide we want to break off and operate on our own, that's an intentional island. And 1547.4 deals with the conditions under which those can come and go from the rest of the grid, talks about how to operate and protect them while they're off grid. I am the chair for the 1547.4 revision working group. So you can go ahead and hit the next slide. And just a little update of what is in this, but we won't get into detail on this simply because of time. Again, anybody who wants to know more about it, please do feel free to contact me. But as I mentioned before, talking about moving back and forth from on-grid to off-grid, the interoperability, and I mentioned interoperability in terms of both power and information. And there are aspects of this that are specific to operation in intentional island mode. So we're going to deal with that. One of the things that we are going to do in 1547.4 is that there really weren't a lot of IEEE standards that dealt with systems that were always off grid, these standalone systems. But a huge amount of what is in 1547.4, since we're dealing with these intentional islands while they're off grid, a lot of that guidance directly applies to standalone systems as well. So we've kind of looped that community into this conversation as well in the course of 1547.4. Next slide, please. Here's where we are on the timeline. As I just mentioned a moment ago, we're in the middle of our working group meetings even as we speak. We are planning to have this standard ready to go to ballot on or before June of 2026. And it says there that it goes to RevCom. Basically, that's the last stage before it's officially published. And we're hoping to do that again on or before June of 2027. I think right now we're actually on a timetable, on a trajectory that will have us able to finish this a little bit early. But famous last words, right? So I believe that was the last of my prepared slides. We can go ahead and go to the next slide. Yes, it is. So I mentioned before, my email address is right here. Please do not hesitate to contact me if you've got any questions about the 2800 or the 1547 standards. More than happy to talk to you about it. And I too offer my thanks to Dr. Juk, who is sponsoring my participation in the leadership of these two standards. Thanks very much. And I believe our next speaker up is Charlie Vartanian.
Thanks, Mike. Going to focus on several tools you can use for those that are adopting and applying 1547. And you'll notice I'm not, a key theme here is use the tools that work more broadly for DER for energy storage when they apply. And a great news item for the industry is 1547 has been thoroughly evaluated and it applies as a technical basis for interconnection performance. The benefit is we all don't have to create technology or even project specific standards for these baseline requirements, well spelled out. Same thing with 2800 at transmission. That was written even more intentionally as a 4-quadrant device or resource standard. So energy storage is covered by 2800. Next slide, please. Thanks, Irene. This is an example of the most critical form of adoption is for retail generation, i.e. customer owned. Investor-owned utilities typically have a published retail generation tariff. In most of the larger markets, IEEE 1547 is referenced. And this really, again, gives all stakeholders this common baseline for the minimum performance requirements. So Will had cited that there are still gaps across North America in terms of state adoption, but I'd say in most of the larger markets that are most active, 1547 is well established. Next slide, please. And here's another tip on tools you can use. California, Hawaii actually preceded the update of 1547 2018 to add grid support capabilities. UL 1741 is the test and certification process published by UL as a standard, and the certification testing can be done by any nationally recognized test lab or NERDL to certify primarily energy storage inverters to 1547. Well, the source requirement documents for California and Hawaii are public, and any energy storage inverter certified to UL 1740 SA, that means it's already been evaluated and verified it conforms. Here's the point. California, Hawaii are moderate to high penetration markets. So these source requirement documents give really good concrete guidance on what are a good set of default parameters on critical control settings for all the performance requirements called out in 1547. Next slide, please. IREC was mentioned earlier. For those adopting, applying, one impact to IEEE 1547 2018 is it has about 10 times the pages of IEEE 1547 2003. So there's a lot more detail in decision making. And these are two really good references to help dig through the standard and see, well, what applies to your project given your particular location and situation. Next slide, please. Another challenge is and working with your local utility, how do you verify compliance with 1547 if that is the technical standard that is being called for? IEEE has this conformity assessment program that's been fairly effective in terms of at the project level, gives a process to assure conformance compliance with 1547. And that's been so successful that IEEE is now setting up an educational program to go out and teach and certify people so they can go through a project, review it, and give a summary report on whether that project is 1547 compliant. Next slide, please. Here are links to the various references. And Zareen, I'm going to put one more link in the our chat with just the presenters. If you could copy that over to the attendees or students. It's a new project that's starting, and it's addresses one of the challenges of interconnection. That is the standards development timeline, the cycle, how long it takes is too long to keep up with the changes in both technology and their application. So you should have a link to an energy storage data guide that was written jointly by Sandia and EPRI. I'm working with Sandia and EPRI right now to see if we can accelerate the conversion of this data guide into a standards document, IEEE. Once an IEEE published standards is out there, it's much, there are, let's say, more established mechanisms for AHJs, regulators to reference an IEEE and ANSI standard versus picking out an industry spec or reference. So if we can convert some of these strong references to standards specific to energy storage, that's going to help hopefully address some of the technical side of the bottlenecks discussed earlier. Zareen, I tried to go quick to leave a little time for Q&A. That does it for me. Thanks for your attention. I'll go to mute.
Well, thank you, and thanks to all the presenters. We could get everyone back on screen here. That would be great, to the best of your ability. And we'll get to some of these questions. We may go a little past 4:30 to try to get to a few additional questions, since we are running a little late. I see Charlie. If anybody else can come back on camera, that would be terrific. Okay. Well, I'm assuming that others are still with us, even though you may not have your cameras on. So I'll go ahead and start with questions. So one is somebody wants to know: are there any states that have fewer interconnection issues? And they say they heard Texas maybe had fewer interconnection barriers, but they're not sure. So is there any state that's sort of doing better at this in particular that we can point to or look at for a model?
Hi, Todd. This is Diane Baldwin with PNNL. I will point folks toward that first volume of the I2X roadmap that has been published that focuses on the bulk transmission level interconnections. There are a number of examples highlighted in there of better outcomes in ERCOT. And I just want to remind everyone, or maybe for those of you who aren't energy regulatory geeks like Will and myself, ERCOT is the Electric Reliability Council of Texas, so operates the high voltage transmission grid in Texas, which is not interconnected to the high voltage transmission grid of any other state, therefore not FERC jurisdictional. So ERCOT has had flexibility in the way they approach interconnection because they have not been bound by the foundational regulations that FERC put in place in the early 2000s, and for large generators, that would be the FERC LGIP, Large Generator Interconnection Procedures. Those foundational regulations have made a much more uniform landscape for transmission level interconnection. So they certainly have been valuable, but have also limited some options. So in general, ERCOT has been shown to have shorter queue times, more projects connecting, more projects in ERCOT than any other place in the United States are interconnected under what we would call at the DER level, that kind of flexible interconnection approach. I believe at the transmission level, they call it connect and manage. And so the idea is, yes, come on to the grid, and there will be times where you will have to be curtailed, but we won't deny you your interconnection, nor will we ask you to pay many, many millions of dollars to upgrade, the conductors on a transmission line. We'll take the approach of come on to the grid, we'll satisfy the safety and reliability concerns. Absolutely, those are paramount. But in terms of some short-term bottlenecks throughout the year, and a few hours here, a few hours there, those projects accept that risk because they have generally been able to make it through the interconnection process and get interconnected in under 2 years.
Great, thank you. The next question actually seems more like 2 questions to me. The person says, is there anyone working on utility oversight by PUCs on ensuring correct and professional work product? There is nowhere to go to get any relief from mistakes, unresponsiveness, or unreasonable charges and fees. So I guess let's take the first part first. Is there anyone working on utility oversight by PUCs that would help them ensure, ensure correct and professional work by the utilities in their interconnection studies and processes? I know Sandia works with PUCs. Is this an issue that is addressed? I don't know if we still have Will with us or if he's left. Charlie says he can't unmute himself. He's muted by the organizer.
Organizers have unmuted me.
Thank you.
A quick comment on the studies issue is using simulation as a basis for going through the interconnection impact process, system impact studies. While people are frustrated with the queuing, it is an efficient way to evaluate versus you can't test a full scale, 200 MVA system. But there's an opportunity, and maybe Michael comment on this. The world of distributed energy resources have been really just relying on equipment certification, UL 1741, maybe project level commissioning tests for larger projects, but there's a real opportunity to move the transmission practice of simulation-based interconnection review and approval into the realm of distribution, and even the idea of cluster studies that it can be combined with the operational flexibility over a wide area and maybe help push through. So there's an opportunity to move the simulation-based practices down into distribution, but that would have to be dealt with state by state. We don't have something nice centralized like NERC and FERC that drives the transmission process.
Okay, thank you.
I can just add maybe one quick thing there, Todd.
Sure.
I didn't get to highlight this because I was kind of, hitting the gas pedal in my presentation, but the I2X program did incorporate an equity and energy justice technical advisory group. And one of the recommendations that came out of that group was built upon some success in Hawaii, implementing an independent engineer that's funded by the PUC, and they're available to EEJ projects or community driven projects, and that independent engineer is that sort of check and balance, so they can review the study results, and they can provide that sort of quality check, and then also some more easily accessed dispute resolution services that don't drag everybody into this long drawn out expensive dispute resolution.
Diane and Todd, I do want to back up and point to 2 specific regions that I do think are setting good examples. The state of Massachusetts opened a proceeding to look at energy storage interconnection regulation. The key thing here is they, from day one, had the ISO New England involved, and that's the regional transmission level ISO, the system operator. And I think that's a great way to avoid unintended conflicts. You don't want a widely separate distribution set of requirements versus transmission. The other region I point to that has solid lessons learned is PJM. Triggered it from their RTO level and reached out and had a set of proceedings involving all their downstream distribution system operators to promote and promulgate what they thought were good technical performance settings that would be applied region-wide. So again, doesn't take care of the queue bottleneck, but these are good practices to put in place to avoid more friction later.
Okay, thank you. Zareen, could you just make sure everybody, all the presenters or panelists are unmuted, just to make sure we don't have anyone who's unable to comment if they want to. Somebody has just made a comment. EPRI is working on an energy storage taxonomy project to advance interconnection, and there's a free report. So if anybody's interested, check that out at the EPRI website. And another question, can a project be in the interconnection queue without a battery storage supplier selected? This is a battery supplier asking this question, and they say, I'm wondering whether I need to include in the sales conversation to prospective customers, are you already in the interconnection queue?
Todd, this
Short
is
answer
Michael
is
Ropp.
no.
Oh, go ahead, Charlie.
Oh, Mike, you please go.
Yeah, I was going to say the selection of the battery specifically has less of an impact than, like, say, the selection of the inverter. You definitely have to have your inverter manufacturer selected because that's going to impact everything in terms of being able to meet the interconnection requirements. What is feeding into the inverter, like exactly which particular battery, is of less impact, but there will be things you will have to redo if you change battery. If you, like, say, well, we think we're going with manufacturer ABC and you end up going with XYZ, that will require certain things in the study process to have to be redone. So you want to try to avoid that if you can.
Okay. Somebody is asking why the utility interconnection studies take so long. Is it a lack of trained people? Are there other factors? They say it seems that this should be something that could be addressed, like the factors should be known and easily accessible to the utility, and the length of time to provide a study shouldn't be so long. How do you address that? Why does it take so long?
Todd, this is Mike from Sandia again. I can speak to that a little bit. Before coming to Sandia, I ran a company for 13 years that one of the things we did was this kind of modeling as a service. We did, many of these, a couple hundred of these kinds of interconnection studies. I think part of the thing is it's going to depend on what your definition of too long is. Usually it took us 6 to 8 weeks from the time we were first contacted to the time we had our final report done. Most of that was actually in the information gathering. We had to get all the information from the utilities, from the equipment manufacturers, from the DER developer. We would develop the appropriate models and then run the appropriate studies. The actual running of the studies was maybe a quarter or so of the total time. The big time sink for us was simply getting all the information together. But I guess I would be interested to hear from the folks on here whether 6 to 8 weeks is quote unquote too long.
Yeah,
It's a lot better than the 2 years we heard earlier in terms of backlog.
Yeah, the backlog isn't the time of the study, though. It's the time waiting for.
No, but there is a lack of trained people to run these, and I think more automation will help for some of the lower level, less esoteric problems. So I know I was working with the Pacific Gas and Electric and basically coming up with procedures to pre-screen areas that had high, I'll call it operational flexibility, and then they could go to a more streamlined process. SoCal Edison did something similar, but Mike, to your point, I worked in the era of early wind and PV interconnection. Probably the number one cause I saw from the utility side where the developers would not turn over the level of detail to run a NERC compliant interconnection study or FERC SGIP, LGIP, and I'd hate to see that happen to energy storage. As an industry group collectively, we should work on having validated models versus having boutique models that vendors won't offer up. And I've seen interconnection processes hung up only because the developer couldn't get the vendor to give a black boxed model over. Now it's a transmission issue. Again, if we solve that problem for transmission and we get simulation down to distribution, we could avoid that problem. And that's another big problem is, Mike, in my experience, the customer information does not have to have supplier specific info, but you have to characterize what type of inverter. Don't have to get into the battery. One of the bigger hangups is, when the developer actually goes out to buy and they get something very different than what was studied, that could lead to a whole another host of reasons why interconnection gets delayed.
There a situation that arises sometimes where the study is done and then the project comes back and reconfigures, and then the study is redone, and there's sort of a cycling back and forth or a negotiation back and forth. So it's not just that it takes so long to do a study, I think, is that it, there is a back and forth that happens, correct, between the utility or between the study and the developer.
Yes.
Yeah, and the more consistency all parties can have through that process, it helps everyone out. It can't help changes all the time, but changes don't midway don't help the process. Major changes.
And Todd, I would add that the group study concept that was mentioned by both Diane and Will can really, really help with this, because as you might imagine, if I'm going to study one plant, I have to know what environment it's in. If that I'm going to then study another plant that's going to be on the same circuit, well, now the first plant is a part of that environment, and that's why it's kind of a serial process in that way. So if we can lump them together, you can do a lot of that in parallel. So that should be pretty darn helpful going forward.
Yeah. Okay. There's a question here about the cost of battery storage. There was a reference. The person says there was a reference by Dr. Juk to a battery energy storage system cost of $180 per kilowatt hour. Where did that come from? And is it total installed cost or just the battery itself without other things like balance of plant and inverter? I don't know if Imre is able to be heard. His audio is disconnected. Can somebody else speak to this? Okay. Unfortunately, his audio is not working right now, so we will go to another question, and hopefully we can get back to this person at another time. Somebody is asking about the potential impact of tariffs. If there are tariffs imposed on imports of lithium-ion batteries from China, what's the impact on these grid queues? Obviously, this is speculative. Anybody care to speculate on this?
I don't know if Will is still on there. I know Will has specifically looked at that issue.
I think he had to go. I think he had another call at 4:30.
Gotcha.
No? Nobody? Okay. We should probably wrap this up. We are almost 15 minutes over time. I've tried to stretch it out a little bit so that we could get to other questions. For those who are asking, the webinar recording and the slides will be made available on the CISA website in the webinar archives. And You can search the webinar archives. It goes back over a decade, so there's lots of information there. This will be posted shortly. I'm going to turn it back over to Zareen to talk about anything else upcoming that you might want to know about. And thank you everyone for attending.
Thank you everyone for joining. We have an upcoming webinar on May 30th. It will be part 2 of our Batteries 101 series. If you'd like to register for that, just go to cisa.org/webinars. Thank you again, everyone. Have a great afternoon.
Thank you, CISA.
Thanks, everyone.